Hello, my name is Andrea Sipos, and today I will be talking about simultaneous contact location and object pose estimation using proprioceptive tactile feedback. To jointly estimate grasped object poses and their contact locations, we make three assumptions: that objects are rigid and geometric models are provided, that the robot can estimate externally applied wrenches using joint torques or external sensing, and that all contacts are point contacts and no moments are applied at contact location. We build upon the contact particle filter to implement the contact particle filter for grasped objects, or CPF grasp. Then, we use CPF grasp to develop simultaneous contact and object pose estimation, or scope. To formulate the base CPF, Manueli and Tedrake note that given a hypothesis for contact location and the polyhedral friction cone approximation, an external wrench applied to the surface of a robot can be inferred from residual joint torques using a quadratic program. While the CPF is limited to the surface of the robot, we extend CPF grasp to an object grasped by the robot, such as the hex key shown here. In order to do this, we assume that the transform between the end effector frame and object frame, HO, is known. Thus, we can find the transform between a contact location particle and the end effector frame. We then use an adjoint transformation to calculate the equivalent wrench experienced by the robot in the end effector frame for a wrench applied in the contact frame. We utilize a quadratic program to calculate the probability that the wrench experienced by the robot, gamma E, is explained by a candidate contact location, RC. CPF grasp also returns gamma C, the contact wrench that best explains the forces and torques at the end effector. CPF grasp was tested in 5 trials on a hardware setup using a Franka Emika Panda arm. Over these trials, CPF grasp localized contact with an average of 4.36 millimeters of error. Next, we utilize CPF grasp to create scope, an algorithm to estimate the contact location and object poses for bimanual robots. It is important to note that scope does not assume that either of the object poses are known. First, object pose particles are initialized for both the poker and the tool. Only the valid particles, constituting a stable grasp, shown in green, are accepted. Second, CPF grasp is run on each object pose particle in the set of poker pose particles and tool pose particles. Third, we compare each poker pose particle to each tool pose particle and score that pair using 3 loss metrics: a penetration loss, a contact consistency loss, and a force alignment loss. Finally, we select the n highest scoring pairs and resample among them, then repeat this method for a prescribed number of iterations to converge to an estimate of contact location and object poses. To validate scope, we ran an ablation study over 10 trials of real robot data in each condition. To directly compare each method, we define an aggregate error comprised of the translation error for each object and the rotation error for each object scaled by the radii of gyration. We find that without all 3 loss metrics, we lose important pieces of context about the interaction. For example, that the objects are in contact and that the objects cannot overlap. Using all loss metrics in this algorithmic framework, scope is able to estimate contact and object poses with low error using only proprioceptive tactile feedback. Thank you.